Hey, good morning.
Morning.
Gabriel, is the microphone on your laptop like a long ways away from your mouth or something? I often have a lot of trouble understanding what you're saying.
Oh, no.
Hey, Calvin, how are you guys doing today?
Pretty good.
That's good.
Yeah, not bad.
Yeah. So hopefully, yeah, I mean, since you're all here, I think you all saw, so the homework will be due next Tuesday, if you didn't see that. So we'll just finish that up today. I think too, did maybe at the beginning of the class, one of you asked something about like COVID or if we would go online. I'm not really, or like the other classes. I can't remember. I think we might have had a short discussion about that on one of the first days, but I'm sure you probably all saw or may have seen the president's email yesterday. But I would say my guess is that there will be some disruptions coming up soon. Just not for this class at all, but I would not be surprised if some of the in-person classes do move to like some kind of online work in the future. So just so you're all aware of that. I also think that though that this time it sounds like the plan would probably be not to like permanently switch over for any of those classes, but to only do it like 1 week at a time or something like that. So anyways, I don't really know for sure what's happening, but I would say definitely start thinking about the fact that there might be that kind of disruption coming up again. So maybe some of your other professors already said that, or maybe you guessed that already, but it seems like it's getting a little more likely now that we're, the president's sending out emails like that. So, but this class is going to be exactly the same. So nothing will change for this one, possibly just on some of your other ones. So, just listen to the announcements, and yeah, that's about it. So we will continue to work on homework 3 a little bit today. Okay, so probably do 1 or 2 of these Gauss's law problems. And what we will be doing, right, so we're on this day, so we'll probably do 1 or 2 of the Gauss's law problems today. Use the rest of the time for the to work on homework 4, and then next week we'll focus completely on homework 4, and then we'll have a review day and the exam. So that's where we're at. Any questions about this class? Yeah. All right, so let's keep going in homework 3. And move on to some of the more specific Gauss's law problems. So this problem, all right, can you see the PowerPoint, everyone?
Yes.
Okay, perfect. So these problems, when you see problems like this, these are problems where we will use Gauss's law based on symmetry. Okay. Right. So basically, we can think of the division. There's a division of 2 different types of problems that we can solve for. So if they're less symmetrical, then use that Coulomb's law cookbook. And then if they are symmetrical, use this Gauss's law. All right. And then all of these questions, you'll do this for all these questions. So both of these are to answer. If you see something that says, find the electric field, okay? So if you see a question that says, find the electric field, basically, there's 2 ways of going about this. One is to use this Coulomb's law cookbook, and that is for the cases that are less symmetrical. So these are the first problems we looked at. Okay, so these problems are the ones where we have point charges, maybe 2 different lines that are perpendicular, but these ones are ones where it's more difficult to find the field because it's the problem is not symmetrical. These ones, if it's more symmetrical, then you can use Gauss's law. So these are usually going to be things like spheres, spherical shells, cylinders, concentric cylinders, and so on. All right. Quick question, based on what you know about superposition, could you solve for one field using this method, and one field using this method, and add them together? Give me a thumbs up if yes, thumbs down if no. All right, I see 3 thumbs up, 4. What do you think, Cade? Mario?
Thumbs up.
Right, so that's correct. You could combine these too. So that's the third unspoken option. You can always combine these. So if you have one symmetrical object and then a few asymmetrical objects, you could go ahead and combine them. But basically, all of these routes are ways of finding E, the E field, and E field follows the law of superposition. So you can always use multiple methods and add them up together. Okay. All right, so that's the reason for this. Now, why do we solve them both ways? So there's a couple reasons. So first, this way, this Coulomb's Law Cookbook, this is basically the pure mathematical way, starting from the like first principles. So this way always works, but can be more complicated, right? You've seen in the cookbook, right? We're dealing with vectors. Sometimes it's a little tricky. There's a lot of steps, right? So this way always works, but you have to really know what's going on with the math, right? You run into some tricky integrals, all kinds of stuff. This route, this symmetrical route, is kind of a more historical way of solving things. And it's just based on noticing that due to the symmetry, the field is going to be constant in a perpendicular direction to your object. Okay, so it's a way of finding some kind of surface. And for us, we're going to be dealing with very basic objects. So we would find these Gaussian surfaces that match our coordinate system, recognize that the electric field is symmetric, that it's perpendicular to that surface, and then solve it using Gauss's law. So this way is a little bit easier. It's a bit of a shortcut. It's kind of a classic or historical way of solving these problems. So before things like the calculators and MATLAB and all this type of numerical integration existed, it's harder to do this route. And so things would be solved more often using this, right? So in engineering, you try to start with the easiest thing and then work your way up. So this way is often easier, kind of a shortcut. So that's why there's the two ways. Okay, now let's go and look at this problem. All right, so first, take a minute and try to draw this. Okay, so on your piece of paper, draw this, draw your coordinate system, draw the thin spherical shell, and think about where you would be able to solve for the electric field, right? So draw this out and think about the different areas that you can solve for the electric field. So I'll give you a few minutes to do that. All right, so how many different places should we solve for the electric field? How many different regions should we look for the electric field? What regions are even possible, do you think? Let's base it off of, we have a sphere. So what's normal? What is the normal orthogonal direction to a sphere? What's if we have a sphere, which one of the three directions is normal to the surface of the sphere? So we got r, phi, and theta. Which one would be normal to that sphere surface?
R.
Or
Yeah, r is normal, right? No matter where you are on the surface of the sphere, that radial direction is normal to it. So let's think about it that way. Okay, so we're looking at it in R. So how many regions of R could we look at? So compared to the size of the sphere, right? We have the sphere has radius A in the R direction. So what regions of R could we consider? Is my question confusing? What do you think?
Yeah, wouldn't it be in all the regions?
Yeah, but there's two, so we have a shell when the radius is equal to A. So if we were to break this up into two places where we could look for the electric field, what would those two places be?
It'd be phi and theta. No, I'm not understanding the.
All right, yeah, so let me clarify. So we have this shell and it has a radius of A. And we want to look at two different areas based on the radius where we can find the electric field. So that would be inside of this shell, right? So this is like a shell, a very thin shell, spherical thin shell. So we could look inside and outside the shell. Does that make more sense?
Yeah.
Okay, so we have two regions based on the orthogonality. So we know that the radius direction is normal to this spherical shell. And we can also guess that the electric field is going to be the same no matter where you are in that radial, or that it will be for a given radial direction, or a given radius, the electric field would be the same at that radius. So that's where this idea of the normal or orthogonality comes from. And then we have two kind of regions. We could find the electric field inside of that shell or outside of that shell, right? And so we could, outside would be when the radius is greater than A, if we were to write this mathematically. All right, and then inside would be when A is greater than the radius. So we should find the electric field in two different places, inside and outside. Now, let's put that aside for a minute and see if we can determine, come up with an expression for what the total amount of charge is going to be. And this is why we call it using Gauss's law. Okay, so let's see if we can find the total amount of charge. And this is coming from the Gauss's law cookbook. Okay, so let me just pull that up for you here. This is on the second page. And we have this integral form of Gauss's law. And so we can see that the electric field is going to be related to the total charge in this via this Gauss's law equation. All right, now, do you remember the relationship between the electric field and the electric flux density? So they're related by the dielectric properties. And in free space, which our problem is, all right, so just looking at this, hopefully you get the feeling, right, that if we could find Q, right, this is the total charge. If we could find the total charge and total charge inside a surface, and then we could find the electric flux density, and we could come up with a relationship between charge and the electric field. So hopefully you get the sense of, okay, we could take one of these Gauss's law equations and get the idea that, all right, we should be able to determine the electric field in a free space dielectric if we can also figure out this total charge. Okay, so that's kind of the idea here behind this method of Gauss's law, applying Gauss's law. All right, so if we want to do this, apply this equation of Gauss's law. We should first solve this integral. And we'll solve this left-hand side here. And while we do this, so in the Gauss's law method, we know that the form of the electric flux density is going to be, right, r hat with some r hat magnitude, phi hat with some phi magnitude, and theta hat with some theta magnitude. Okay, now we have a spherical, this is where the idea of the symmetry comes in. So we have this spherical shell of charge, and we now need to think about the symmetry that comes in this. So what is the magnitude of each one of these? We should be able to think about the magnitude of these and realize that some of the magnitudes are going to be 0, right? So some of these directions, some of the electric field will not have any magnitude, right? So which one of these 3 are going to have 0 magnitude? Or put otherwise, which direction? There's only one direction that the electric field will be pointed in, and what is that direction for a sphere?
R.
Yeah, and can you explain a little bit how you knew that? Was that Mario too who said that?
Yeah, that was me.
Thanks, Mario.
Well, basically you have the R always pointing in different directions, and then phi and theta don't really end up changing. They're always constant.
Yeah, and they're constant in the direction of actually not pointing at all in phi and theta. So yeah, very, very good. Thank you. I'll show you one other way of thinking about this for a sphere, right? We know, right? Remember, for a point charge, if this is just a point charge Q, do you remember what the electric field looks like? Just, it's always pointed like this, right? Out from the charge. Right, so it has some r hat direction and some magnitude, but there is none pointed in phi, right? So this would be, depending on the coordinate system, right? This would be a phi direction. And then in the other way, I don't know what coordinate system we're in, but right, it's pointed directly out from the charge. And so just like a single point charge, if a sphere is going to have the same effect where the field is always just in that one direction. So we get this symmetry from it, right? So this is that point charge. And remember, this is the derivation of the electric field for a single point charge. Okay, so that's just a quick aside. So we can now guess, right? We can now guess that for our spherical shell, we can now guess, and even more than guess, we can know that the electric field will just be in this one radial direction. So we can now say that we have a form for the electric field. So we don't know what this is, right? We don't know what the magnitude is, but we can find it later, right? So we can find the magnitude of this later. And then what about the ds? What ds should we be using for this problem?
Would we not use the one for R?
Yeah, we'll use the one for R. And how did you know that?
Because we already talked about it moving in the direction of R.
Yeah, exactly. So we know that our field, right, is pointed in the R direction. We're trying to find a surface, right, that we're going to move around on. And when we move around on the surface, the movement on the surface is in the phi and theta direction. So we should have our R as r hat r squared sine theta d theta d phi. Okay, so now we should be set, right, to solve this. So we're trying to solve this equation. All right, so on your paper, try to solve this integral. All right, so on your paper, solve this integral. And my first hint is going to be, if I take this dot product, right? So this is a vector, and this is a vector. If I take the dot product of vector A and vector B, is that going to be a vector or a scalar?
A scalar.
Yep, so when we take the dot product, it's going to be a scalar, and these vector directions, r hat, right, they're going to go away. All right, so take a minute on your piece of paper and solve this integral. All right, so take the dot product and then solve the integral. So what should the limits be what should the limits be on theta and phi?
Uh, 0 to 2 pi.
Which one should that be? Theta or phi?
Phi.
Yep, that's correct. And what about for theta. Definitely starts at 0. Should it go to pi or 2 pi?
Should go just a pi.
Yeah, that's correct. And that's if you go all the way, this is kind of more of a math problem, but if you go all the way to 2 pi, you would actually be going back around and doubling that sphere amount. Okay. All right. Did anyone get an answer for this already?
Yeah, you just end up getting 4 pi r squared.
All right. 4 pi r squared. And is there anything else that should be in there?
So why are we using pi for theta? Sorry, I missed that.
Yeah, using pi for what?
For theta.
Yeah, you only use pi for theta. This is a little bit of an aside, but let's take a look. Let me see if I can pull this up. One moment. Okay. All right, so this is your spherical coordinates. And if in order to get the full sphere, you only need to go from 0 to pi on theta. Now, the reason for that, let's take a look at this. So this one's phi, right? So if we start at the x-axis and go all the way around for phi, right, that goes from 0 to 2 pi. Okay. Now for the theta, choose a different color here. Can you all see that this is theta? If we took a slice like this, a half slice of the green, took a half slice of the green and then wrap it all the way around 360 to 2 pi, right? That's going to make a full sphere. But if I went all the way, if I went too far, right? So this is 0 to pi, but if I went all the way to 2 pi, then that'd be a full sphere rotating all the way around. And so I'd get double what I expect. Does this explanation make sense to you, Daniel?
I'm still having trouble getting it. So 2 pi is a full sphere, but why are we getting double if we, like, I don't know. I don't get why.
Okay, so let's imagine like half a circle here. Make this bigger. This is one tiny thin slice, okay? It's infinitely thin. And if I want to find a full sphere, all right, this is a half slice. And if I want to find a full sphere and I rotate this infinitely thin half slice from 0 to 2 pi, that will give me a full sphere, right? Does that make sense?
Yes, it does.
Okay. If we rotated a whole sphere 360, you would get twice as much on accident. Right? Does that, so if you did a full sphere and rotated it 360, you would accidentally get 2 times as much sphere as you meant. So that's where those limits come from.
Oh, so we are we are operating based on the fact that we rotate the sphere.
Yeah,
Okay.
yeah, that's where we get the limit from. So we want the full surface that we're trying to find. It will be all the way around in phi and then halfway around in theta. And that will give us that full spherical surface. All right. Okay, so that's where the limits came from. That's good. Now, is there anything missing from this?
Yeah, I forgot the DR.
Yeah, that's correct. So the DR, right, we're integrating on this time. So the DR should also be there. All right, perfect. Perfect. So now we got this and this, right? This was equal to Q. So this is also equal to Q. All right, so now we're starting to make a little bit of progress here on our problem. So now we said, right, we said we'd find this later, right? So now we're getting close to later, and we can write by rearranging an expression. We can write an expression for dr as q over 4 pi r squared. Okay, now we're starting to get somewhere, right? Because remember, our goal is to find E everywhere. And we know that E is equal to this. And we know that the electric flux density only has one direction. So it's in r hat, and it was, right, dr. Okay, and we just figured out what dr, an expression for dr in terms of q, right? So we have this q over 4 pi r squared, right? And that came from this. Okay, so we're starting to get somewhere, right? So any questions so far about how I got to this expression? All right, so now we have an expression for the electric field, and the only thing we don't know in the expression is Q, right? And what is the meaning of Q? That's the total electric charge, right? So it's the total electric charge inside of a region. So we said that we would come up with expression for the total electric charge inside of the sphere and the total electric charge outside of the sphere. So let's start with the inside and determine the total amount of charge inside of the thin spherical shell. So without using calculus or anything, what is the total amount of electric charge inside of this spherical shell?
Maybe 0.
Yeah, there's no charge. There's no charge, right? It just, all we know about the problem is that there's a thin spherical shell that has a charge density. And as far as we know, there's no other charge, right? So for the first case that we came up with, right? When the radius is less than a, right? Q is equal to 0. So that must mean, right, going back to this equation, right, that this Q is equal to 0. So the total electric field, right, is equal to 0 inside of the sphere. Oops. Inside of the spherical shell. All right, now what about when the radius is greater than A? What is the total amount of charge then? So if we're outside of this shell, what's the total amount of charge contained? So if our radius, if we think of a sphere that's larger than our shell, so something that totally wraps around our shell. So if we came up, we just set our limits, right? And we're all the way out here. We've contained all of that charge. How much charge is included on that shell? And if you don't know, how would you find out how much charge is contained in that shell? What type of mathematical operation should we do?
Integral of the
Yeah, we should do an integral, right? We should integrate that surface to determine what the total amount of charge is. Okay. So somehow we should do this integral. All right, so we have a total charge or a charge density, and we want to, and it's on a surface, and we want to add that all up somehow. So how should we go about doing that? We're going to need to integrate over a surface again. So we're going to need some ds, right? Do another surface integral. So we should have this, and the ds is going to be the same thing, right? In this case, right? Because we're going all the way around that spherical shell. So again, our limits are going to be 0 to pi and 0 to 2 pi. All right, so take a minute and do this integral on your paper. And once you've got it, let me know.
I got an answer.
All right. What is your answer?
It would just be that rho s r squared 4 pi.
All right. Yes, that is correct. And then one more thing, what is the value of R? So on that shell, what is R equal to?
The A.
Yep.
Yeah, the a.
Yeah. All right. So if we then just put that into our equation, right, we would get that the electric field is R hat 1 over epsilon naught. And then we got 4 pi r squared on the bottom. And then on the top, the Q is rho s a squared 4 pi. So we get a little bit of canceling out. And we have rho s a squared over epsilon naught r squared. As the answer for the second one and the first one. All right, nice job, everybody. Does anyone have any questions about this?
So as far as the second answer goes, it's only correct if A is greater than R, right? No?
Yes, that is correct. Yeah, when R is exactly equal to A, we have not contained any of the charge because it's infinitely thin. I get, yeah. I guess at A that does include the charge. I'm trying to think how this would work. Yeah, let's just say there's the two regions because when R is equal to A, right, we have not, our field has not actually gone on to include the charge yet. So we have inside of the sphere and outside of the sphere. And that spherical shell is just infinitely thin. All right, so I won't solve the last one, but let's just think about the steps on this so that you can solve the last one on your own. All right, so basically, right, you have the left-hand side and you have the right-hand side. And you solve this side once, right? And then you solve this side for each region of interest. And in the other problem, right, you have a few different regions of interest. You have two different regions of interest as specified. And also in that last problem, when something's grounded, you won't have any field outside of that structure. So, but I don't think you actually need to know that for that problem. Okay, so let's move on to homework 4 a little bit. Unless you have any questions. All right. So homework 4, problem 1, this one tells us some voltage, which is the electric scalar potential. All right, so sometimes we call the voltage the electric scalar potential. And the question says, what is the electric field in these regions? All right, so we know the electric scalar potential, and then we're saying, let's see if we can find the electric field. All right, so there's a relationship between these, right, which is that the electric field is equal to this, right?
I'm Dr. Christlight. If you are writing, we can't see it.
Oh, thank you. Can you see this up here where I wrote?
Yes.
Okay, all right, perfect. All right, so we should be able to tell the relationship between these by using this expression. All right, now, okay, so this is saying, right, that the gradient of the scalar field is equal to that electric field with a negative negation, right? So this is a scalar, right? This is scalar. And then this is the del operator, right? And so if you take the gradient, right? The gradient takes a vector. I'm sorry, takes a scalar and it gives you a vector. So for this first one, right, we can see that it's in that X direction. So and because this is X direction, right, we can see, we don't know anything about how the voltage changes in Y or Z. We just know how it changes in X. Oops. Oh, yeah, sorry. So for 0 to 3, right, we're just looking at this and we are determining what the derivative is of that problem. So, right, we can just do this as the rise over run. So delta V X dy dx. So from 0 to 3, right, this is 30 minus 0 and 3 minus 0. So X is equal to 10. And because E is equal to negative del V, right, this is going to be minus X 10 volts per meter. And I can solve for this, right, for each part of this, right? So this is the answer for region 1. Now, what about for this second region? What is the slope here?
0.
Yeah, so in the second part, E is equal to 0. And then What about for the third part?
-10.
Yeah.
Sorry, I was wrong.
Is it negative or is it going to be positive?
It's gonna be negative.
Yeah, the slope is negative, and then the electric field will then be positive. Does that sound about right?
Sorry, can you explain where that negative comes from? Like, I mean,
Oh.
yeah, up there.
Okay. That comes from the fact that if we have a positive charge, that's pointed like this, and a negative charge, the field is pointed like this. Okay, and so we could draw lines of constant potential. Do you know what I mean when I say that?
Just how they're interacting with each other.
Yeah, so so this electric field right all the way around here, right? It's going to be constant in these directions. Like around this. And so let's see. So what this is saying is that the slope, the electric field is actually the negative of that slope. So if the gradient is positive, right? So if we have a positive slope, then the field is actually pointed in the other direction. But if you have a negative slope, then the field is pointed in the opposite direction of the slope. Does that give you more understanding?
Yeah, that helps a bit.
Okay, it's really coming from the idea of we could have positive charge or negative charge where the field is pointing in or out, and really we're mostly dealing with I guess electrons being negatively charged, and so that's where that distinction comes from. Okay. The absolute, it's kind of weird though, because right, the absolute potential is the same, right? And potential is like the difference in energy. And so this is almost like whether you're measuring, like, imagine you have your multimeter, right? You're measuring your voltage on your benchtop, right? You have multimeter, you have a black and a red. It's just whether which direction. Do you have the black on the bottom and the red on the top, or did you reverse it? And so in some way, and then if you reverse it, right, you'll still get that same absolute potential, the same absolute voltage difference. It's just whether or not you put your black like on the common and the ground or not. And so that negative comes from the idea that it should come from the idea that the negative charge is what we're normally dealing with. So that's the long answer. The short answer is this is just the equation. How's that? All right, and then what about in region 4? Do we have any slope in this region?
No.
Yeah, it's back to 0. And then in 5, we should be back up to this. All right, and we could draw this. Right, you could draw the electric field just in one, the magnitude of the electric field. So EX in the X direction, and it would go from -10 to 0 to 10 to 0, like that. 10, 0, -10. Where this is 3, 5, 11, 13. Okay. So in some limited cases, right, you can go back and forth between the potential and the voltage pretty easily. And in this problem, you should be able to do the same thing. So you just need to figure out what the sine wave is on both of these. And then you should be able to, right, you should be able to take the derivative of that sine wave. Now, we can also do this, right, in a little more detail, right? So we can do a problem like the second problem, right, where we actually have an electric field, right? And then we could determine what the voltage is. Okay. So we could go the other way. If we had an electric field, we could determine the voltage. And we can write this. So this is like saying the voltage at 2 with respect to 1. All right. So this is saying, right, if we took a path through an electric field from one point to another point, we could find the potential difference between the two. That's what this is saying. So this is like saying if you have your two probes on your multimeter, right, you can put it down at one point on your breadboard, and you can put the other probe down on the other point of your breadboard, right? And it does not matter what path you take through your circuitry, right? You could have 10 paths on your circuitry from point 1 to point 2, but it doesn't matter, right? Because your multimeter probe is just measuring the difference between the 2 points. It doesn't matter what the path is that you take, right? You can take any path. You're just measuring the difference between these two paths and coming up with a voltage, which is the electric potential between the 2 points. All right, now in this problem, it's a little bit easier to break this down into two parts, right? Because we have this electric field, right? And this is like a point charge, right? It looks kind of like a point charge's field. And why would I say that? Just because it's only in the R direction, right? We only have one direction. So this field, it looks like it's just pointed out from the center of your coordinate system. When we integrate, it's along the z-axis. It's often easier to change into the Cartesian coordinate system. So I could change this, right? If we had a Cartesian coordinate system, right, with the z-axis like this, when you're above, when z is greater than 0, right, the electric field is pointed up. But when z is less than 0, right down here, the electric field is pointed down. So if I converted this into Cartesian coordinates, we would have this expression for when z is greater than or equal to 0. What about when z is less than 0? Can you see if you can figure out what the expression would be? So if we're converting this to Cartesian coordinates, so we want to put it into z hat form. What is the expression for the electric field when z is less than 0?
Isn't gonna be along the negative direction?
Yeah, so it's the same thing, except it's negative. Right, so it's just a negative in this case. All right, so this should help you to find this, because in both cases, right, you will have DL. What will DL be equal to? If we're integrating along the z-axis, what is DL?
Z.
Yeah, it's in the z direction, and this is a vector, right? So should be z hat dz. Let's see, one last point for part B. You might want to break this into three integrals in order to simplify this a bit. So one of them might go from -4 to 2, -4 to -2, and then -2 to 0, and 0 to 2. And two of these might cancel out. So but there's more than one way to solve this, but that was the way I solved it. All right, we still have a couple more minutes. Does anyone have any questions on homework 3, homework 4? Okay, well, we will look at another voltage potential problem on Tuesday that's a little more complicated. Do take a look at the Moodle page if you haven't already, because I put up something that I think will help you. Okay, so I put up this, where'd it go? I may have loaded it into the wrong spot. Oh yeah, okay. Take a look at this Coulomb's law cookbook solution. Okay, so this is a solution to a classic problem to find the electric field for an annular ring. And in homework 4, we're going to take a look at, we're going to try to find the voltage potential due to this annular ring. So the more you understand this problem, the easier it will be to find the voltage potential of that annular ring. All right, and when I say annular ring, right, I just mean it's this circular ring of charge that has a radius of b, in this one plane. And so that sometimes is called an annular ring. All right. So take a look at that before you do homework 4 next week on Tuesday. Quiz 3, homework 3. Those are due at the beginning of class. So we'll start class on Tuesday right around 8:20. If you have any questions, I will stick around on this Zoom call. And if not, I will see you all next week. So have a nice weekend.
Thanks, you too.
Yeah.
Thank you, you too.